So for the rest of chapter 9, we're really going to be talking about the physical properties of solutions. So I'm on page 19, and I've got these concentrations. I've got, that's methanol, ch09, 1 mole per liter. If I were to think about the solute particles, I'd say, well, there's 1 mole per liter. And you're thinking, so what? Well, here's vitamin C, 1.60 moles per liter. I have 1.60 moles per liter of particles in solution. Ammonia, that's a teeny bit of a fib, but it's pretty good. Ammonia, that's 0.50 moles per liter. I've got 0.50 moles per liter in solution. And you think, okay, Wallace, I don't know what you're doing. You're just saying, yeah, there's the concentration, and you're writing down the concentration over here without really thinking about what the particles are. You're just saying, well, yeah, it was 1 mole, 1.6, 0.5 moles per liter. So what? So lithium chloride, 1 mole per liter. When I look at the particles in solution, of course, I have 2. Well, wait a minute. Okay. Potassium sulfate, 1 mole per liter. Well, it's got to be just 1. All right, well, what about this sodium phosphate, 0.2 moles per liter? It's just got to be 0.2. And it's 0.80. So what's going on with those things? Well, let's go back and think about this. When I put this CH3OH in water, it dissolves. It dissolves really nicely. When I put sugar in water, we know C6H8O6 aqueous. When I put lithium chloride in water, I get lithium ion aqueous plus chloride ion aqueous. Notice what I'm getting. I'm getting like 2 for 1. Stop the video and figure out how sodium phosphate would break up compared to those numbers. All right, you did it, right? You said, oh, I remember from chapter 3 and chapter 5, this would be 3 sodium ions plus 1 phosphate ion. I'm getting 4 for 1. Well, these are electrolytes. Strong electrolytes, in fact. But what strong electrolytes do, or what all electrolytes do, first of all, they dissolve in water. But they break up into ions. Break up into ions. Now, this means a couple of things. The concentration of the ions, the moles per liter of ions, is greater than what's on the label. In other words, I had lithium chloride, 1 mole per liter, but the concentration of ions was actually 2. And so what's really in the bottle, the concentration of the stuff that's interesting to us, concentration really equals the concentration of the ions. And this is, again, I just want to remind us, we're talking about electrolytes. So electrolytes. Now, there's another really important property of electrolytes, but I'm going to have you stop right here. I've got these 2 videos in the Canvas assignment, so watch those, and then we'll come back and pick up page 19 at the beginning of page 20. All right, you watch the videos, right? Well, in the video from Berkeley, you saw non-electrolytes in water and strong electrolytes in water. And what you noticed about the electrolyte solutions is they conduct electricity. So electrolytes dissolve in water, break up into ions. Consequently, the concentration that we talk about is really the concentration of the ions. The concentration of the ions is greater than what's on the label, and that solution itself conducts electricity. So let's look at page 20, and we can line it up, and we can talk about sorting all this out. So strong electrolyte examples. NaCl is a strong electrolyte. KBr is a strong electrolyte. FeNO3 is a strong electrolyte. Now I'm going to go over here and say non-electrolytes. CH3CH2OH dissolves in water, but it doesn't do the things electrolytes do. That's ethanol. SO2 dissolves in water, but it doesn't do those things. SiH3F. C12H22O11. CH3CHOH CH3. Non-electrolytes. I guess I should come back over here. Strong electrolytes include these: HCl, HBr, HI, HNO3, H2SO4, and HClO3. These do those things in water, form those solutions. They behave like electrolytes. These don't. Now, let's go down here and say, well, no, let's complete this table. Now, weak electrolytes. Now, this is a little bit fuzzy. I'm going to say HF, HCN, HNO2. And there are many, many, many more. AgCl solid, BaSO4 solid, FeCO3 solid. These dissolve in water, form ions, the solutions conduct electricity. These dissolve in water, they don't form ions, they don't conduct electricity, and this is something in between. Well, they dissolve a little, they form a few ions, conduct electricity a little bit, which then brings us down to this table here. Strong electrolytes, ions in solution? Yes. Non-electrolytes? No. Weak electrolytes? We'll get technical. A little. Not much. Does the solution conduct electricity of strong electrolytes? Yep, we saw the videos. Sugar, these other compounds? No. Do these weak electrolyte solutions conduct electricity? Well, we haven't seen that demo, sadly, but a little. Not much, but a little. Now, what I want to do is go back and say, well, wait, okay, what kind of substances were those and those that were strong electrolytes? Now, you might stop the video and say, well, what do those have in common? What do those have in common? Well, what it is, if I go back and look up there, soluble ionic compounds, soluble ionic compounds. Chapter 3 and 5, coming back to haunt us. Ionic compounds, metal and non-metal, and they're soluble. Chlorides, bromides, nitrates are soluble. Now, what about this group right here? Do you recognize those from, say, Chapter 4, Chapter 5? Yes. Strong acids. Put either any of those things in water, they dissolve, they form ions, they get that conductive solution, and the concentration of the particles is sort of greater than the label. Over here, I'm going to give you a hint. Polar molecules. Remember chapter 4? Polar molecules will dissolve quite nicely in water. They won't conduct electricity. For Chem 51, they'll dissolve, they won't form ions, and they won't conduct electricity. Now, I want to give you a couple of examples for the medical field. Alcohols are commonly in that category. Those are always going to end in OL, isopropanol, methanol, ethanol, butanol. And the other one is sugars, and they always end in OSE. So anything that's sucrose, glucose, mannose, lactose, oh yeah, this is going to dissolve in water, but the solution is not going to behave like a strong electrolyte. All right, and in between, well, this gets fuzzy, but we can say for sure weak acids. They dissolve in water, they form a few ions, and they conduct electricity a little bit. And then this is where it really gets fuzzy for Chem 51, and I'm just outright lying, but it's going to be okay for 51. I'm going to say insoluble ionic compounds. Now there's lots of gray area there, and we're pushing the sort of boundaries of definitions, but that's okay. We're going to say, okay, insoluble ionic compounds, weak acids, weak electrolytes, dissolve a little, they form a few ions, they conduct electricity a little bit, concentration of ions is a little more, or concentration of particles is a little more than what the label says. Okay, there you go. Let's stop there for this clip. So, since we're talking about this new situation where the molarity or the concentration inside the solution really is not the same as what the label says, we have to come up with a new term. So we had said molarity is moles of solute per liters of solution. Now we have this thing osmolarity, which is moles of all particles. So we can take a solution and just say, I don't care if it's ions, molecules, atoms, add everything up. Well, this becomes very important for strong electrolytes especially. So here I've got 0.67 moles of magnesium chloride. Now I recognize that as soluble, and it's a strong electrolyte. It's a soluble ionic compound. So I have to remember, when I put magnesium chloride solid in the presence of water, I get magnesium ions plus 2 chloride ions. Remember, this is where chapter 3 is coming back to haunt us. If I don't recognize it, oh yeah, chloride doesn't stay together as 2. Chloride breaks up. Those are 2 individual things. So I might do this like this: 0.67 moles of magnesium chloride, and I want to get to total moles of ions. Moles of ions. That's what I'm trying to get to. I can say, okay, moles ions, moles MgCl2. Well, I'm getting 3 for 1. 3 for 1. Stop the video if that doesn't make sense. Think about that. That gives me 2.0 moles of ions total. Now let's calculate the osmolarity. Osmolarity always sounds like it'd be an excellent name for a heavy metal rock band. I have to recognize, oh yeah, that's a strong electrolyte. In water, I'm going to have K+, aqueous, and bromide aqueous. So I'm getting 2 ions for every 1 mole of KBr. So I could formally do this. I could say, okay, 0.35 moles KBr per liter times 2 moles ions 1 mole KBr equals 0.70 osmolarity. I think sometimes that gets shortened to OSMOL. Here's a trickier one. Glucose. We said sugars like that are non-electrolytes. They dissolve in water quite nicely, but 0.15 moles per liter of glucose is 0.15 moles per liter particles. Here, however, what am I going to multiply that by? Stop the video and figure out, okay, wait, am I going to multiply this by like 7 or 2 or what? Stop the video, you figured out, oh, I'm getting 3. I'm getting 2 potassiums and 1 sulfate. Remember chapter 3? So I'm going to multiply that by 3. So I could say, oh, my osmolarity 0.15 plus 0.050 times 3 gives me 0.30 osmolarity. Again, if that doesn't make sense, stop. Think about that. How to get the 3? Why did I break that up? What did I need to know from chapter 3? Now, in a medical situation, here I'm telling you everything I don't know about blood and that biology stuff. But so I guess there's blood, which is a solution, and there are blood cells, which must be these little spherical things sort of floating around in there. So when the osmolarity of the blood is equal to the osmolarity inside the cell, we say it's isotonic. And the blood cells are happy for reasons that we're going to see later. If the osmolarity of the blood sort of around the blood cells, we say this is hypertonic. And for reasons that we'll see later, the blood cells are unhappy. It can be destructive. If the osmolarity of the blood around the blood cells is less than what the osmolarity is inside the blood cells, we say that's hypotonic. Again, it's not good for the blood cells. And we're going to talk about that the next 3 pages in lectures. We're going to talk about properties of solutions.